Here we are with section 2 of chapter 7, classifying chemical reactions. I'm actually going to split this section into two videos. In this first video, we will cover these first 3 or 4 learning objectives regarding classifying chemical reactions and focusing in on precipitation reactions and acid-base reactions. In the second part of this section 2 video, I'm going to focus in on oxidation reduction reactions and that last learning outcome. Go ahead and stop the video now and write down these learning objectives in your notes, and then we'll get started. Okay, when we talk about classifying chemical reactions, sometimes it helps to think of it in two ways. One way is kind of the mechanism or how the reaction works, which will allow us to predict the products. And the other way is a classification of the type of reaction. So you see I separated those two on the screen here. So let's first focus on the mechanism. And that is basically when I'm given a reactant, can I look at the reactants given and determine or predict what the products will be based on its classification here and kind of the mechanism of how the reaction works. Okay, so you can see that if I just go down the left-hand side there, I'll see that they all look very different on the reactant side. So for example, a synthesis or combination reaction has a generic form of A plus B yields AB. That would be something like this. So magnesium plus oxygen yields MgO. Obviously, I would then have to balance it. But you can see what a combination or synthesis reaction looks like. A decomposition reaction is basically just the opposite. So instead of starting with two reactants, we're going to start with one compound. And that compound is going to break up into its two atoms. You have to be careful here when you do this. Don't forget about Hofbrinkel. So this bromine would actually get that subscript 2 because it's a diatomic, which would then require me to balance it like this. The next type is a single displacement or single replacement reaction. You can see here I have an element and a compound, and in this case I have two metals, A and B. And what's happening here is B is currently the cation bonded with the anion, and if A is more reactive, then it'll bump B out of there, then form a bond with the anion, and B would be by itself. An example of a single replacement reaction would look like this. So now magnesium, there's something called the activity series of metals. We don't need to worry about that just yet, but magnesium is more reactive than the hydrogen. So it would bump the hydrogen out and I would get magnesium. Again, I have to think of the cation and anion and do the crisscross method to get the MgCl2 here. Plus hydrogen is now by itself. Also, don't forget Hofbrinkel. It gets a diatomic 2. And then I would balance it like this. Next, we have a double replacement or double displacement reaction. Okay, here we have 4 ions, 2 cations, 2 anions, and to produce new products, those ions need to rearrange. So as I know ionic compounds, the cation is written first, so A would be positive, B would be negative. And in the other compound here, C would be positive and D would be negative. Okay, now to produce new compounds, I'd have to rearrange. So the only option that A would have to get something new would be to bond with D. And then therefore that leaves the C bonding with B to form new products. So here if I had something like potassium chloride and calcium phosphate, and then rearrange those ions, the potassium would go with the phosphate and the calcium with the chloride. Okay, and then of course, like always, I would need to make sure that this is balanced. Just like that. And the last type of reaction, as far as mechanism go, that doesn't fit into any of these categories that I've listed here, is a combustion reaction. Combustion is a type of oxidation reduction. We'll take a look at that later. But it's basically any hydrocarbon, combinations of carbon and hydrogen, reacts with oxygen to produce carbon dioxide and water. So this part of the combustion reaction is always the same. And then it just, what changes is the hydrocarbon that you start with out there. That's why I've labeled it CXHX. We've already seen some of these in our balancing practice because, as I mentioned in the last video, combustion reactions, depending on the ratios and combinations of carbons and hydrogen there, can get a little tricky. So they are good practice when we're practicing balancing equations. That's one way to classify chemical reactions, and it's helpful for me to be able to look at the reactants, see what I have on the reactant side of the arrow, and then be able to predict what's going to happen to get the products. Two single elements combining to form one compound, two compounds, so rearrange the ions to form two new compounds, and so forth. The other way we classify reactions is helps us determine if a reaction on paper is really going to happen. So this work that I just showed you over here with the mechanism, I could do those all day long on paper without any real understanding or knowledge of, does this reaction actually happen, right? So the best scenario would be being in a lab and mixing compounds and chemicals together and then seeing if a reaction happens. A precipitate forms, it gets cloudy, a color change, things like that. We don't always have the ability to do that, so it's helpful if still on paper, I can work with a chemical reaction, predict the products, and then be able to say, based on what's being produced here or what's happening, this is a reaction that will in fact occur if I were in the laboratory and put these things together. So we often refer to this second type here, the classification, as driving forces. They help me to identify or indicate that a reaction is going to occur, even though I'm working on paper here, so I can move forward with understanding why that reaction is occurring. So let's jump in here with precipitation reactions. Okay, so a precipitation reaction is one in which a solid product is formed. So if I can do, these are going to be double replacement reactions. If I can rearrange my ions to predict my new products, and if I can then identify if one of them would be a solid, then I know I have a precipitate and a precipitation reaction, and I know that that's a reaction that's going to occur. So a couple key terms here that you'll hear. Again, this is an exchange of ions and compounds. We have to start thinking about, when I see that notation aqueous after a compound, I should no longer be thinking of this as a compound KCl. That aqueous tells me that this is ions. This has been dissolved into ions. So I have potassium ions and chlorine ions, not the ionic compound KCl. We have to do that when we're doing reactions to free up those ions so that they can then maybe potentially form with other ions and form precipitates. And then we would see a reaction. The terms soluble and insoluble, you'll see us refer to as we're trying to determine if those predicted products are solid or not. If something is insoluble, then that means it's going to be a solid, and we'll get that designation S after the compound. Okay, we have to become familiar with these general solubility guidelines. There is also a table that I've provided you, but you're not going to have access to that table. So while the table may be helpful to quickly take a look at while I'm doing practice problems, I need to really be able to be comfortable and have these general solubility guidelines down and memorized. Here's our goal here. Here's what we're trying to do. You get aqueous potassium iodide is mixed with aqueous lead nitrate. So we want to take a look at this reaction. We want to predict the products, and we want to determine if this is a reaction that would actually happen. Okay, so As I've said before, I always like to quickly write down the ions present because I'm going to use those in a couple different ways. So if I just take a second to jot those down, I know I'm not going to miss something or make a mistake. Okay, so now I'm going to put the reactants together, the potassium iodide, and again, these are aqueous. It tells us that in the problem, but I would know that in order to get this reaction to happen potentially. Okay, is mixed with our lead 2 nitrate. Okay, so now I'm going to predict the products, and in order to do that, as we saw before for a double replacement reaction, I'm going to rearrange the ions. So this positive potassium ion can only be with this negative nitrate ion. So as I cross those charges, and so I'm going to very deliberately here put those parentheses where I'm going to identify the state of that compound and leave it blank for now. After I've predicted both products and balanced this out, then I'll turn my attention to trying to determine what state that KNO3 is, and I have to do the same thing for the lead 2 iodide. Okay, so I've predicted the products. As we know now, we always have to balance, so quick look at this, should balance it like that. All right, so now I can turn my attention to the states. If either one of these, KNO3 or PBI2, are insoluble, then that means I have a reaction, and I'll continue on from this, the molecular equation, to the complete ionic equation and net ionic equation. If neither of these are insoluble and they're both aqueous, I'd be done here and I'd just be saying there's no reaction. Okay, so as I take a look at these guidelines for solubility, if I see here in number 2, I can see that right here that nitrates are soluble. So that tells me the KNO3 is a nitrate and it is soluble, so that gets the AQ notation. Okay. The next PBI2 is an iodide. So as I look at rule number 3 here, chlorides, bromides, and iodides are soluble except for those, and we have one of those exceptions, PBI2. So that means PBI2 is insoluble and it gets the solid designation there. Okay, so that's my classification. This is a precipitation reaction. So this is a reaction I can now say, even though I'm working on paper here and I'm not in the lab putting potassium iodide with lead 2 nitrate, I can say with some confidence here that this is a reaction that's going to occur. So from there, I'm going to move from my molecular equation, that's my molecular equation, and I'm going to do my complete ionic equation. Okay, as if you remember, a complete ionic equation, I'm writing out all the ions present. So everything that's listed as aqueous here needs to be broken up into their ions. And that would look like this. Just a reminder, the solid stays together. It has precipitated out and has formed that solid, so it is no longer as ions. Everything that's labeled as aqueous is broken up into its ions. Once I've done that, you'll recall I want to cancel out or cross out my spectator ions. Those are those ions that appear on both sides of my arrow. So in this case, that would be the potassium and the nitrate ions. Once I have canceled out my spectator ions, what I'm left with is my net ionic equation. And so that, at the end of the day, is what's really important about this reaction. The reason why in a lab setting we saw a reaction occur, in this case a precipitate form, was because I had lead ions and iodide ions in solution. Okay, how they got there in these two compounds that we dissolved and made aqueous solutions isn't as relevant, because those ions cancel out. They remain in solution, my spectator ions. So this is really why we saw a reaction occur here. The other type of reaction we're going to talk about in this first part of the 7.2 video are acid-base reactions. Acid-base reactions happen when there is when a hydrogen H plus ion is transferred. We know from our naming of acids that an acid is anything that has an H plus to start. So you can see I've listed here the strong acids. This is going to be an important list for us down the road to know and memorize, because to be a strong acid means those ions disassociate or break up completely. They break up completely. Okay, so in this first reaction, we are going to get a 100% split of the H plus and the Cl minus, because HCl is a strong acid. That only occurs for these strong acids. Weak acids do not disassociate completely. So I'm not going to spend a lot of time, although it's covered in this section, I'm not going to spend any time in this video or at the moment talking about weak acids. But just to know at this point, if I had a weak acid, I would actually change the yield arrow to a double-sided arrow like this, because I don't get a full reaction to completion like I would do with a strong acid here. Okay, so right now I'm just going to focus on strong acids and that complete dissociation. So what you see happens here is the transfer of a hydrogen from the HCl to the water and the production of the hydronium ion. When we get to acid-base chemistry, we'll talk a lot more about the significance of the hydronium ion. A more common or a type of acid-base reaction is a neutralization reaction. This is similar to what we saw with the precipitation reaction as far as a molecular equation, a complete ionic equation, and a net ionic equation. So what happens here is our ions exchange, right? So I have two compounds. So I have magnesium 2 plus and hydroxide OH minus. So there are my four ions that I have here in solution. And those ions, the magnesium, it says solid here, but we'll say it's been dissolved in solution. Those ions are going to rearrange, and I'm going to get the MgCl2, and I'm going to get H2O. Now notice the H2O has this designation of a liquid here. Okay, so similar to what we did with the precipitation reaction, that's what's important. This is a reaction that we can say with confidence is going to actually happen, because like a solid in a precipitation reaction, water or a liquid is formed in an acid-base neutralization reaction. We could even go as far as to do the complete ionic and net ionic equation, and the net ionic equation would be nothing more than this. And that's why what's important here about the neutralization reaction. Okay, so that's all we're going to cover here in this first video for section 7.2. In our next video, we'll focus solely on the third type of reaction, oxidation reduction reactions.